Section 5.8, we're going to talk about an average value process. And we have a equation or a formula, I guess you would say, which calculates the average value for a function from A to B. So what it does is it takes the antiderivative from A to B of your function, the rate of change function. You find the antiderivative, and then you divide it by B minus A. And another way to write that is to do that division of the 1 over B minus A out in front, and then do the antiderivative notation between. Now, you've seen this notation. You saw it back in, I should highlight it like that. You've seen this notation all like this back in 5.2, where you did a lot of like verbal descriptions of what it was. Do y'all remember that? You said things like from 1992 to 1996, the average number of employees changed by not average number, but the employees changed by this number. You did some things like that. You did some calculation, but not calculations. You did some verbal descriptions, interpretations. Let me actually show you what this means to do algebraically, because we haven't talked about that part yet. So the 1 over B minus A is exactly the same in the front. It's this piece that I want to clarify for you. What this piece says is it says find the antiderivative. We're going to call it f of x with a capital F. We talked about that notation last time. And we're going to evaluate it. So this vertical bar is an evaluation bar. We're going to evaluate it at the top value, whatever's on the top of that evaluation, which is a B, and at the bottom value, whatever's the bottom of that evaluation, which is our A. And what that literally means we're going to do is we're going to plug in B into the function, capital F of x, and we're going to plug in A into the function, capital F of x, and we're going to subtract them. It's the ending value minus the beginning value. That's what it is. So in terms of the one that's on the board right now, that's what I have written on the board. The ending value, n of 6, minus the beginning value, n of 1. And that tells us what the new number, in that case of that problem, of employees was. And then if we multiply that times 1 over B minus A, we'll be able to get the average, again, if we're talking about the problem I just have on the board right now, number of employees. The average of whatever it is we're looking for over that time span. So the calculation part of this is not too bad. And in fact, I do hope you have your calculator with you today, not because you need it for your quiz, but because I'm going to show you a really cool trick, provided that my screen will work, or I'll have to just show you how to write it in their calculator regardless. I don't know. I've been having some trouble with that. Maybe there's only 2 chords coming out of it. We'll give it a try. All right, so let me actually show you what's going on the first problem we've got anyway. U.S. factory sales of electronic goods to dealers from 1990 to 2001 can be modeled by this equation. So we've got a cubic equation here. It's billions of dollars, years since 1990. It says use a definite integral to approximate the average annual value of U.S. factory sales of electronic good dealers from 1990 through 2001. So it's wanting us to calculate this quantity. Okay, this new formula that we're dealing with together. So to start with, we've got this component at the beginning that's 1 over, and it's the difference in the values, and this is from 1990 to 2001. So how many years is that? 11. That's 11 years. So if you want to write down 2001 minus 1990, you can. If you want to put more specifically, since 1990, 11 minus 0, you can. But it's the difference of 11 years. So we're going to get an 11 when we subtract however we decide we're going to write that. Now my integral is in fact supposed to go from the year 1990, which should be represented by a 0, because I'm measuring things since 1990, to 2001, which is an 11, because 2001 is 11 years after 1990. And my function itself goes here next. It's a doozy. I'm going to use it from over here because I can't keep scrolling in and out. So it's 0.0388x cubed minus 0.495x squared plus 5.698x plus 43.6 dx. That's what we're calculating. Space. Yeah. Okay, I'm just putting it on my new screen because I have more space to work it out over here. All right, so we're going to find an antiderivative. The same things you're going to do on your quiz today. We're going to do the 1 over 11 at the front. We'll get to that later on. I need to take my 0.0388. I need to increase the power by 1, so my 3 becomes a 4, and divide by the new power of 4. And I'll do the same thing on the next one. It's the subtraction. 0.495. It was x squared, now it's x cubed over 3. My 5.698, it was x. So now we increase the x to the 1 by 1, so I have x squared over 2. And then my 43.6 becomes 43.6x. And then technically, what do I need next? I need a plus c. Now, I say technically because I don't actually need it here, but I want to show you why I don't need it here before I just say, you don't need to put it here now. All of a sudden, it just disappeared. It's going to disappear for a reason, and we aren't going to actually need it on these problems, but I'd like to show you why. Okay, so is everybody good so far? All right. At the very end of this, where I don't have any space, so I'm going to shift it over one more time, we're going to put that evaluation bar with the 11 on top and the 0 on bottom. Now, 0 is an awfully nice value to plug into this, because what happens when I plug 0 into all of this function? You get 0 on everything except for the c at the end, right? Yeah. So think about what's happening here. I'm going to plug in 11. I'm just going to call it capital F right now, of 11. And then I'm going to plug in the 0. And when I do that, I'm going to get a plus c in both of them, right? Everybody with me? There's going to be some numerical value that the calculator is going to number crunch for me, and it's going to have a plus c at the end. And the other one's going to have 0, because when I plug in 0, it all goes away, and then it's going to have a plus c at the end. So at some point in here, I'm going to end up having a c here, and I'm going to have a c here, and what's going to happen when I subtract them? Yeah, 0, right? They're going to cancel each other out, because one's going to be a positive c in there, and the other one's going to be a negative c in there, and I add them together, and they become 0. So I'm not going to actually end up getting any of these c's that are here because of that. Now, here's what I expect to see. What we've written so far, I expect to see this piece here like that. That's where you're going to start, okay? You don't necessarily have to have the c here, because we recognize that as we add it into both pieces, it's going to go away. So the other pieces of it you can put, and it will look like this. I don't want to do that way. I'll just leave it there. Okay. So I'd like to show you some cool calculator tricks. You ready? Okay, so obviously you could put this equation, the one you just found, into y1, and you could evaluate it at 11, right? We've done that kind of stuff before, no problem. So I could put in the calculation that I created, right, that I found, and I could tell it, plug in 11 and see what happens. Are you with me? This is yes. Okay, fabulous. But what if I made an error in my calculation? What if when I created these numbers, I screwed something up, and so now it's going to continue on in the problem that I screwed something up? Yeah? And that's a possibility. And we wouldn't know it, that it happened, because I used the calculator to calculate something, but the calculation error itself was in my work earlier on. So what I'd like to show you is how you can do it without actually using the piece that you created in case you did make an arithmetic error. So I'd like you to hit y equals. And I'd like you to put in the original equation right here. So you're going to put in 0.0388 x to the third minus 0.495. I don't think it's plugged in. Just check real quick. Well, that's not plugged into anything. On my computer, but my computer won't display then. Okay, I'm just going to walk you through it without having to show you. I'm sorry. All right, so minus 0.495x squared plus 5.698x plus 43.6. So does everybody have the equation that we started with, the original equation in y1? Yeah? Okay. Exit your screen, just go into the regular screen like where you would add numbers together or multiply or whatever. And I want you to do math 9. So one option that happens when you hit math 9 is that it says FNINT. Okay, if that's you, I'm going to walk you through what to do next. And if that's not you, I'm going to borrow somebody's calculator and I'm going to walk you through their calculator what to do next. So if yours says FNINT, what you're going to do next is you're going to put in there y1. So you hit vars, yvars, function y1. You're going to put a comma, and you're going to put in the value x, because you're saying x is my variable. You're going to put in another comma, and you're going to put in your lower limit of integration. In this case, it was a 0. So your new comma, 0. You're going to put another comma, and you're going to put the upper limit of integration here. It's 11. Close your parenthesis, press enter. And it will tell you, again, if this is yours, you're still a 1 over 11 at the beginning, but the value inside the brackets is 746.7317. Okay, so who has the other operating system that I can borrow your calculator real quick? Paula? Okay, thanks. Okay, yeah, that's what it looks like. I couldn't remember. Okay, Paula already figured it out as she went through it because it's so nice and friendly in the other version. It actually shows a script S when you hit that math 9 with some boxes. You put your boxes to match these. So the lower limit goes here, your upper limit goes here. Inside here, you're going to put y1. It already gives you a D, and here you're going to put an X. Okay, that's the other operating system, which you did it just fine. And it'll still tell you 746.7317. Thank you. Okay, did anybody's calculator not try this? You did all the steps, or you thought you did all the steps I showed you, but it didn't come out as 746. Did anybody's not give them that? What'd yours do?
I got a negative 212.
Okay, let me take a look. There it is. Awesome. Okay, anybody else's? All right, anyone else's calculator giving them something different? Yours does, Jacob? Okay. miss. I'm so sorry that happens, but yeah. Okay, and the last thing you would do in this problem then is you would divide by the 11 that's here, right? So here, just hit divide by 11, and it's going to give you, so actually doing the divided by 11 part is going to give us 67.88. And it's whatever the units were to begin with. Let me actually talk through that a little bit with you. It said it's in $1 billion. So I'm going to put the word billion. You can write $1 billion at the end, or you can put the word billion at the end and the dollars at the beginning. What you need to recognize as you're doing this is that the reason that I end up with the units being the same is because I'm actually both taking I'm dividing by my number of years here, right? That's what this is doing. And then when I take an antiderivative, I take off the per years. So I'm putting in a per years and I'm taking off a per year, so my units actually end up the exact same as what I had before. This is billions of dollars. Now I want to show something else really cool on your calculator, but you're going to have to walk through it with me. You already have the equation in Y1, right? So I'd like for you to hit your window button, and I'd like for you to make your window button go from 0 to 11. That's the time span we're talking about here in years, right? Let me see what the zoom fit actually gives me in terms of a picture before I tell you to do it. Yeah, it'll work. Okay, so after you hit window from 0 to 11 on your X min is 0, X max is 11, hit zoom 0. That's zoom fit. And when you do, your graph is going to end up looking something like, it'll have a dotted line at the bottom, like this. And it's going to have a solid line over here on the right, the left-hand side like this. And then the graph looks kind of like this. Does everybody's screen look like that? Okay. From this screen, I want you to hit second trace. We've been in the second trace menu many times. This is the calc menu. We've seen zeros, we've seen maximums, we've seen minimums, we've seen the intersection feature. We've even seen the dy dx, but we haven't done that very much. What I'd like for you to look at is number 7. Number 7 says script f, this is number 7, script f of x dx. Do you guys see that? Okay. I'd like for you to just press number 7. On the bottom of your screen, it says lower limit. Our lower limit's 0. So type 0 and press enter. And then it says upper limit. That's 11. Type 11 and press enter. What happened? It shaded it in, right? We talked about this back in 5.2. It's a video you watched. I didn't actually do it with you in class. About the fact that we're finding area under the curve, right? This visually is fabulous. It actually shaded in for you the area under the curve. And not only that, but it has that same answer, 746.7317 on the bottom of your screen. Now, the caveat to doing that is we had to make sure that our window is set up properly. So if you're a really visual person, you just make sure your window is set up properly, and you can use that feature to find the calculation that we just did. Or you can find the calculation in your regular screen by using Math 9. Either way will give you the same answer. Part B is very interesting, though, because Part B wants us to sketch a picture. Well, we've already drawn the picture sort of here at the bottom corner. I'll draw it over here a little bit bigger. Here is my actual graph, and I'm going to actually make my window now go all the way down to 0. So if I hit window and I make my Y minimum 0, it will actually shift my graph up so you can actually see what it should be when it's not a dotted line at the bottom. It actually looks like a much less steep graph than what I had before. It looks something like that. Does your graph look something like that? Okay. In y equals, I would like for you to put your answer in to y equals, like the actual answer when we divided by 11, the 67.88 billion. Is that what it was? We had 60. Is that what we had? Yeah, 67.88. I should have written 88.5. I'm so sorry. Should have been 885. In Y2. Yeah. So in Y2, you should put in 67.885 and graph it. And what it will do is it's going to create a horizontal line about like that, give or take. Okay? Do you see that horizontal line cutting through it like that? So what is it actually doing? Well, it's taking this curved graph that you have and it's basically leveling it off into a perfectly horizontal line that has the same amount of area underneath. So if I were to find the area under my curve that it did just a moment ago, here in yellow, right, like this, and I were to find the area under the curve from that horizontal line down, I'll do it in pink, so like this, they would be exactly the same. It's almost like Play-Doh, right? When you mush the Play-Doh, you don't change the volume, but you change the shape. I've taken this two-dimensional shape and I've evened it out to be a horizontal line that has the same amount of area beneath that it had beneath the original irregular type function that I was dealing with. So when I'm looking over here at finishing out this graph, I'll label everything. This is in $1 billion. This number was at 67.885, right? That's that horizontal line I just drew. This went from 0 to 11, and this was years after 1990. Okay. Our last question we'll go through much more quickly. Most of it's things that we've seen and done before now, since it's the second question. Go over here and you have a table. This is the most expensive rates in dollars per minute for a 2-minute telephone call using long-distance carriers are labeled in the table below. I've got the years 1992 up to 2000. So anytime we're dealing with years as the input, we want to align our data, just so that we're all doing the same thing. Let's just make them 2, 4, 5, 6, 7, 8, 9, 10, 15, and 20. So in y equal, or not in y equals, you can clear out y equals though. In stat edit, we're going to put in those x values with the corresponding rate as the y values. So 2, 4, 5, 6, 7, 8, 9, 10, 15, and 20. And then in L2, we have 1.52, 1.24, 1.14, 1.01, 0.83, 0.77, 0.65, 0.55, 0.35, and 0.2. We'll look zoom 9 at my stat plot. Oh, make sure your plot's on. Mine's off right now. Let's turn your plots on if they aren't. Zoom 9, and you look at the graph. Once you get to that point, what graph might be good to try? What's it look like? You got a bunch of dots on your screen. What does the dots shape look like? We did this back in chapter 1. Y'all know lots of equations now. What do the dots look like? Exponential is a very valid point. Are there any others that you could think to try, Jacob? Maybe a quadratic? Exponential seems like it would fit the ending behavior better, probably. So let's try exponential first. So in your regular menu, you can hit Stat, Calc, EXPREG is number 0, and put it into Y1. I'm going to graph it to see if it fits the data pretty well. And it actually fits the data really, really well. So even if quadratic's good, it's not going to be any better because this is such a good fit, and this fits the end behavior. So this will be our model. This is the rate. I'm going to call it little r of x. And the equation that I have is 1.916 times 0.892 to the x. In the table, the output units are dollars per minute. And my x values, my years, this were measured since 1980. So x years since 1980. And the data values themselves that I put in started at 2 and went to 20. So that would be my model. So part 1A, rather, is the same thing we did back in section 1.11. Part B, use the definite integral to estimate the average. That's what this section's about. So it wants us to do it from 1982 to 1990. So that's a span of 8 years, or we could say 10 minus 2. So we're going from the year 2 to year 10 of 1.916 times 0.892 to the x dx. So this is 1/8 in front. The antiderivative should be the 1.916 0.892 to the x. And then we're dividing by the natural log of 0.892. That's my antiderivative. And I'm supposed to be evaluating from 10 down to 2. It's already in Y1 in your calculator, so you can either look at it from a graph point of view and do second trace, or you can go back to your regular screen and do Math 9, function Y1 from 2, to 10. And I've got that 1/8 in front, but the calculation is 7.976 that it spits out at me. So if I divide that by 8, I get 0.997. That's my 3 decimal number. But my output is supposed to be in dollars. So I need to round this off. So how will this round? Down to 99 or up to $1? Yeah, it'll round up to $1. So this is $1 is my average phone call length, or phone call price between those 2 years. Part C is the same question. It's just asking me to do it from the year 1982 to 2000 instead. So instead of going from 2 to 10, I'm going from 2 to 20. Of the same thing I had before. And then I've got 1/18 in front. I have the same antiderivative I had before. Evaluating from 20 down to 2. So I can do Math 8, and I just change my, or Math 9, excuse me, I just change it from 2 to 20 instead. The beginning I have 1/18, but inside I have 11.597. If I divide by 18, this is a dollar amount, so it gives me 0.64 cents, or $0.64, which is 64 cents. And that's what we would have if we span the time between 1982 and 2000 instead of 1982 and 1990. Which makes sense because the prices went down dramatically during that last 10-year time frame, right? Indeed. Any questions on that? Okay. A lot of calculator stuff. because you have that very nice feature of being able to calculate the input values. You do still need to show the antiderivative every time you're asked to take it. Okay? You're showing the antiderivative step, and then you're allowed to use your calculator to do the input of the values of the variables. All right, so this assignment will be due on Tuesday.